Okay, welcome to the second video about section 4.4. Actually, this video is covering what the book actually covers in 4.4. In the first video, we just reviewed how to simplify square roots so that won't be a problem in this section, hopefully. So today we're going to start talking about imaginary numbers, okay? We have so far only worked with real numbers. Equations, like we'll see in a minute actually, led mathematicians to define what we call the imaginary unit I. Okay, so basically I is the square root of -1, because when do we run into trouble with square roots? Well, if I tried to take the square root of -4, up until now we've said there's no real number that meets that, because there's no number times itself that gives me -4. -2 times -2 is +4, and 2 times 2 is +4. So what mathematicians did to be able to work with these kind of numbers is they defined I to be the square root of 1, which means that I squared is -1, because the square root of -1 times the square root of -1, according to the rules of square roots, gives me just -1. So the important things to remember are I is the square root of -1, and I squared equals -1. Okay, those are called the imaginary. I is the imaginary unit. So when I have numbers that look like this, 6 times I, -2 times I square root of 3, those are called pure imaginary numbers. Pure imaginary numbers are square roots of negative real numbers. So this actually means 6 times the square root of -1, right? So for example, if I want to take the square root of a negative, then I just rewrite it as the number times the square root of -1, and I replace the square root of -1 with I. So let's simplify the square root of -28. We're going to do this very similarly to what we did in the previous video that we looked at, except we have a -1. So I have -1 times 2 squared, or times 4 times 7, because 28 is 4 times 7, and 4 is a perfect square. So I write all of those things out, and I replace the square root of -1 with I. The square root of 4, or the square root of 2 squared, is 2, and then the 7 stays under the square root. So I write that as 2I times the square root of 7. So when I have a negative number under a square root, I basically rewrite it. I bring out that square root of -1 and rewrite it as I, and then I simplify the rest of it just like we did in the last video. Okay, same thing for the square root of -32. That's going to be a -1 times 4 squared, or 16 times 2. 16 is a perfect square. The square root of -1 becomes I. The square root of 16, or the square root of 4 squared, is 4. And then 2 is not a perfect square, so it stays under the square root. And I have 4I times the square root of 2. So I want you guys to try this one. Your answer here is C. And there is the work if you need to look at that. And then I want you to try this one as well. Simplify the square root of -45. The answer here is A. And here is the work for that one. All right, so when we're talking about I, it's important to understand how the powers of I work. So we already know that I to the first is just I, which is the square root of -1. And then we already talked about how I squared is -1. Well, the rest of the powers work just like powers would with regular variables or regular numbers. I cubed, I can rewrite it as I squared times I to the first. But I know that I squared is -1, right? So this is really -1 times I, or -I. I to the fourth is the same as I squared squared, or you could think of it as I squared times I squared. Well, I squared is -1, and I squared is -1. -1 times -1 is +1, or -1 squared is +1. I to the fifth is I to the fourth times I. Well, over here we learned that I to the fourth is +1. +1 times I is just I, and so on. Make sure you understand how all of these work, but any power of I can be broken down just like this. So let's look at this example here. We want to simplify -3I times 2I. Well, we multiply just like we would multiply -3x times 2x. -3 times 2 is -6. I times I is I squared. But because we know that I squared equals -1, -6 times I squared is -6 times -1, which is just +6. All right, let's look at this one. The square root of -12 times the square root of 2. There's something very important here. Pull out the i's, or rewrite it with i's, before you multiply. You have to pull out the i's before you multiply. So the square root of 12 is, remember, the square root of -1 times the square root of 12. And this is the square root of -1 times the square root of 2. Square root of -1 is I. So this is I square root of 12 times I square root of 2. I times I is I squared. The square root of 12 times the square root of 2 is the square root of 24. And then we simplify like we have been doing in previous problems. So that gives me I squared is -1. The square root of 4 is 2. And then the square root of 6 just stays the square root of 6. So that's -2 times the square root of 6. Super important to pull out the i's first, because if you don't, if you just multiply these, you would say, well, -12 times -2 is +24. So this is the square root of 24. And you would miss this negative that belongs out in front. Because the problem is that both of these represent imaginary numbers. So that's why we have to rewrite them as imaginary numbers before we multiply. Otherwise, we lose that negative. So you have to do that. Okay, try this one. The answer here is -15, and there's the work for where we get that number. And then try this one, the square root of -2 times the square root of -6. The answer here is B, and there's the step-by-step work for how to get to that answer. Okay, now sometimes what we've been talking about up until now is solving quadratic equations by graphing or by factoring. And I can solve that way when things are like ax squared plus bx plus c equals 0, as long as a is not 0. But there are some quadratic equations that I can solve using the square root property. And I can solve those if they look like ax squared plus c equals 0. So I don't have that x term. So if b is 0 and it looks like this, I can use the square root property because I just have to get the x squared by itself, and then I can square root. So let's look at this. I have 5y squared plus 20. This is a quadratic equation because of the power of 2, but in this case my b is 0. So I'm going to subtract 20 from both sides, and then I'm going to divide by 5, so I get y squared equals -4. So because I just have a y squared, not a y squared and a y, I can take the square root of each side, right? So I can take the square root of y squared, and I can do plus or minus, don't forget that point, the square root of -4. The square root of y squared is y. Here I have plus or minus the square root of -4. And now that we have imaginary numbers, instead of saying no real solution, we will simplify them as far as we can go. So the square root of -4 is the square root of 4 times the square root of -1. The square root of 4 is 2. And the square root of -1 is I. So I have plus or minus 2i. So what this means, because this is an imaginary number, not a real number, it means that my parabola would be floating up here above the x-axis. It would not have any real x-intercepts. It has 2 imaginary roots. Okay, try this one. The answer here should be a plus or minus 5i. And there's the work to show you how to get to that answer. Okay, what we're going to do now is we're going to talk about something called complex numbers. A complex number is any number that can be written in this form. So I have a real number a plus or minus an imaginary number b times I. So a complex number, this is one single number that has a real part and an imaginary part. So here I have 5 plus 2i. They're not like terms because one is real and one is imaginary, but together they make up one complex number. Here I have 1 minus 3i, so 1 would be my real part, and -3i would be my imaginary part. So any number that I can write like that is called a complex number. This changes a little bit our number diagram. So before, we only worked over here in the real numbers. So we worked over here in the real numbers. Real numbers were split into rational and irrational. And then my rational numbers were split into integers, natural, and whole numbers. Well, now we have a whole nother section. Complex numbers are actually the set of all numbers we can work with, and complex is divided into real and imaginary. Real numbers are the ones we're already used to: rational, integer, natural, whole, and irrational. Whereas imaginary numbers are these pure imaginary numbers that look like b times I, and then complex numbers represent the entire set of numbers. Two complex numbers, this is important for our next example, are equal if their real parts are equal and their imaginary parts are equal. So if I have a plus bi equals c plus di, a has to be equal to c, and b times I has to be equal to d times I. So let's look at this example. I want to find the values of x and y that would make this equation true. In this equation, I find my parts with I, and those are my imaginary parts. So I know those have to be equal. Then the other parts that do not have I are my real parts. So what I'm going to say is, okay, if this is going to be a true equation, 2x has to equal negative 14, because those are my real parts. And then y times I has to equal negative 3 times I, because those are the imaginary parts. So x has to be negative 7 if 2x has to equal negative 14. And y has to be negative 3 because I already know that the i's are equal. So in order for yi to equal negative 3i, y has to be negative 3. So that when I plugged my negative 7 in here, I would end up with negative 14 plus negative 3i, which is equal to negative 14 minus 3i. All right, you guys try this one. Okay, the answer here should be D. X is 5 and y is negative 2. All right, when we add and subtract complex numbers, it's pretty easy. We just add the real parts and we add the imaginary parts. So basically here we're saying, okay, I'm going to have 3 plus 2, right? So we have to add those. And then 5i plus negative 4i, which they show us right here. So that ends up giving me 3 plus 2 is 5. 5 minus 4 is 1, so I have 5 plus 1i. I can do the same thing with subtracting. So I'm going to do 4 minus 3 and negative 6i minus negative 7i, which is negative 6i plus 7i. And that gives me positive 1 plus 1i. All right, try this one. The answer here is D, 5 plus 10i. And try this one. Here your answer is B, 5 minus 3i. Okay, sometimes an application of complex numbers is electricity. When we're talking about electricity problems, they usually use J to represent I. I'm not really sure why, to be honest with you. But we will see these problems sometimes, and that italics J means the same thing as I. So in this example, they give me a formula. They say that the voltage E is equal to the current times the impedance. Okay, so they just give me this formula. They're saying find the voltage with a current of 1 plus 4j amps, so that would be my I, and an impedance of 3 minus 6j ohms, so that would be my Z. To do this, I just have to plug into my formula and multiply. To multiply, here we just FOIL like we normally would. 1 times 3, 1 times negative 6j, 4j times 3, 4j times negative 6j. That gives me this result right here. Remember that j squared is going to equal negative 1 because it's just like I squared. Here in the middle we added our like terms. And when I simplify, I get 27 plus 6j because negative 24 times negative 1 became positive 24 plus 3, which is 27. Okay, you guys try this one. The answer here is B. And there's the work for that one. All right, last but not least, just like with radicals, to simplify imaginary numbers that are in the denominators, we use the conjugates. They're called complex conjugates. Because remember, I can't have an I in the denominator because I represents the square root of negative 1, and I'm not allowed to leave square roots in the denominator. So here we're going to multiply the numerator and the denominator by the conjugates, and we're going to multiply. And then we're going to simplify, remembering I squared is negative 1, and this would be our final answer. So I want you guys to try this one.